So hello everyone, welcome to today's GoTo seminar. This is going to be about ultrafilters by Starý. Here you go, it's yours.
Well, thank you for inviting me. Not to scare anyone. First of all, we're doing this in English, I suppose, right? Not to scare anyone off, the ultrafilters will be only the final touch on a finite set. So the ultrafilter will be the all-powerful tool that decides everything in the end. But you don't need ultrafilter combinatorics to understand this. I will introduce everything. The proofs are mostly elementary. The topic is Kenneth Arrow's theorem on voting systems. That's originally from the 50s, and his motivation was economical, like putting money or something or casting a ballot in an election is an order of preference. It's voters casting their order of preference. So first we will formalize that, and then we will prove the theorem, which says that in any sane election procedure, there is a dictator, a single guy who decides everything. That's the thrilling version of the theorem, but of course I'll state it formally once I get there. So let me start with the formalization. We will have a set of voters and a set of candidates. They will be finite in the end, but I don't need that now. So let's say I have a set of voters and I have a set of candidates. And I will formalize what an election is now. Okay, so okay, so how do we formalize that people vote? So let's say every voter casts some bijection from let's say from the set of candidates onto the set 1 to n. Okay, I already need that there's finitely many, but all I need is that it's a linear order. It wouldn't have to be finite. So we have finitely many candidates, and to vote is to cast a bijection on the set of candidates. You are number 1, number 2, number 3, number 7, right? That's what voting is. And what is an election? An election is such a choice. Let's say capital E will be set of all elections, which says that this voter has assigned this candidate this position, where every let's say E B, I will denote it like that, is a bijection, which is a vote. Okay, so this is what an election is. Okay, now this is how people cast their ballots, but then you have to decide globally what the overall result is. Who's the winner of the election? There's already something that you could have objections to this already, because you might only care about the absolute winner. You don't need people to specify a total order. Also, people might not care about each and every candidate. Conceivably, you might prefer Alice to Bob as a candidate, but you don't care about Charlie and David. So it wouldn't have to be a bijection and therefore a total linear order on the set of candidates. It could be a partial order. You could generalize, but let's stick with that. Now, what is the way to decide the overall result of the election is called an election procedure. So an election procedure is what gets such an election and says what the total order, the eventual order is. Okay, so this maps the set of elections onto this order bijectively again. And we will say that yes. No. Yes. Because the result maybe I messed up the notation. The result of that election on the, oh yeah, oh sorry. Okay. What I want to say is that the result of the election maps this candidate A over candidate B. This will mean that the result, okay, I'll need to fix the notation. The result prefers or favors A over B. Okay, so if it's this mapping that I need to, okay, this is the set of all elections. So this is mapping from this to, yeah, so it's okay then. This is okay. From, okay.
E times C2.
Okay, E times C2 the bijection. Okay. Okay, so there's natural conditions, mild, sane conditions on such an election procedure, such as if everybody votes this way, the result should be this way. That's called unanimity. That will be one of the sanity conditions. Also, if people vote for Alice over Bob and the result says Alice wins over Bob, then in another election where more people vote for Alice over Bob, the result will still favor Alice over Bob. That's called monotonicity, etc. So let me list these conditions. Let's say sanity conditions. Of course, a prime example would be simple majority. If more than half people vote like that, the result will be like that. Okay, so sanity conditions on such an election procedure. First of all, unanimity, which is to say, do not oppose a unanimous vote, respect a unanimous vote. So sanity conditions. So in any election, for any two candidates, let's say A, B, Alice and Bob, if everyone in their ballot prefers A over B, then the result of that election will prefer A over B. Respect a unanimous vote. Unanimity. Second, monotonicity. If in another election more people vote like that, keep that result. So formally, for any two elections and any two candidates, if if that will be a horrendous formula, so let me write it in words. If everyone who preferred A over B in that election, look at it like a second round, like a first and second round of the election. If anyone who preferred A over B still prefers A over B, and the result for any other candidate is the same for any C which is not, or which is a candidate other than A and B, and the original result favored A over B, then this second round also favors A over B. The formula is horrendous, but the notion is natural. Only more people now vote for Adam over Bob. So the winner should still be Adam if it was Adam before. That's called monotonicity. And thirdly, independence. The idea is that the relative position of Alice and Bob does not depend, only depends on how people voted about Alice and Bob, and is independent of how people rated Charlie and David. So independence, that says for any two elections, for any two candidates, say A and B again, if in this election a voter preferred A over B, exactly when they preferred A over B in this other election for any voter, then if the result of the original election preferred A, then the result of this election also prefers A. That's called independence. If Alice wins over Bob, then Alice still wins over Bob. If, sorry, that's, right, that should be right. Okay. It only depends on the position of Alice and Bob, not anyone else. That doesn't say that they are ranked the same. If in my first cast ballot, Alice is my number 3 and Bob is my number 7, and in the other ballot, Alice is my number 9 and Bob is number 12, this condition is still satisfied. But their relative position is the same. Then, if Alice is favored, then Alice is still favored. So that's independence on what? Independence on the position of the other candidates. Okay, so turns out that these 3 suffice to state the theorem. These are obvious sanity conditions. Let me also put in the definition of a dictator. Who's a dictator now? A dictator is a voter whose ballot decides the election. This single guy, his vote decides what it is. Okay, so voter B is a dictator for this election procedure if for any way people casted their ballots, the result of that election is how he voted. That's a dictator. Now the theorem, every election procedure does have a dictator. That's the theorem. If the procedure is same and there's at least 3 candidates. Homework immediately. Find the 3 counterexamples, the 4 counterexamples. If the election procedure is not same, breaking unanimity, breaking monotonicity, breaking independence, and the theorem does not hold, and if there's 2 candidates, what happens if there's only 2 candidates? Okay, so theorem, Kenneth arrows, if the set of voters and the set of candidates are finite, as happens to be the case on Earth, and there's at least 3 candidates, then any same procedure, any same election procedure, meaning the three conditions, has a dictator. So that's what I'm going to prove. To call it a dictator is a bit of a misnomer or a bit of a cheap trick, a cheap thrill to make it sound more thrilling, because let's say there's candidates ABC and I voted ABC in that order, and the election result happens to be ABC. That makes me a dictator by definition for any election. If that happens for any election with a procedure, that makes me a dictator. But it's not like I pronounce myself a dictator beforehand and stated my result will be the result. No, it just so happens that your voice happens to be the result. And any guy who casts the same ballot is also a dictator, though. Not to belittle the theory. Okay, so I'll need a bit of formalization to build the ultrafilter that I want to talk about eventually. Okay. Okay, so let's, before I get to the proof, it will take like 3 lemons. What's the time? Oh. Okay. Okay, so first, a bit of notation for any election. let me denote by that, like the preference in this election of A over B is exactly the set of those voters who preferred in their vote A over B. If you've ever seen the proof of Walsh theorem in model theory, you know where this is heading. Like the index is where it holds. Okay, and let's say that a set of voters is decisive for A over B if they can make it, if they can force it. That is to say, for any election, if they prefer A to B, then the result will favor A to B. So, for any election, if these guys prefer A to B, then the result of that election will favor A over B. So that's what it means to be decisive for A over B. And stronger notion, to be decisive, period, if it is decisive for any pair, for any or any distinct pair. Right. Those are, you could call them the kingmakers. If we vote Alice over Bob, then Alice will win over Bob. We can do it. We are the decisives. Okay. Now, first of the technical lemmas, how do you find out if a set is decisive? First of all, by the unanimity, like the set of all voters obviously is decisive for anything. But how do you find the minimal one? If the set, there are decisive sets, obviously, the set of all voters, the whole electorate is decisive. So given a finite set of voters, a finite set of candidates, there's complexity questions already, which I will not go into, but there's finitely many possible elections, finitely many possible procedures, so find a decisive set which is minimal. The 7 of us do decide, but any 6 of us do not decide. That's a minimum set. What's the algorithm to find the minimal decisive set and how hard is it? I will not go into that. Okay, so first of the lemmas. For any set of voters, the following are equivalent. Firstly, the set is exactly the preference set of A over B. Oh, sorry. For there is some election for which X is the preference set of A over B, and the result is indeed A over B. And secondly, for any election, if X is the preference set, then the result will be A over B. That's a characterization of how you find out whether a set is decisive. The definition wants that for any election, if it is at least you, then it will be the result. Here's a characterization. Well, if you find one election where you are precisely those guys voting for Alice over Bob, and it happens to be the result. This is the same thing. Proof is simple. Okay, so put which is which, A and B, B and A. Okay. So let B be preferred over A for any E prime for any voter who is not in that set, if you are at least that set, we'll make it precisely. Oh, this is, oh, of course, this is a proof of the easy one. If you are decisive, well, it means if it's at least you, then that will be the result. We'll make it exactly you. Like switch the ballot between A and B for anyone not in your group. Thanks. That's it. It will be the result and it will be precisely the preference. The real one is this one. If you have one election where it happens like you said, then you can decide any election. Well, that is by independence, because let E be such that you are the preference set of A over B. Now we need to show that that will be the result, and let let's say E0. Oh, should be another name. Okay, so let E0 be the good one, namely the election where it happens, right? Okay, so tweak that election to be something else, namely be such that this is then okay, then and the preference of A over B in this election is exactly the preference in this election, and then by independence, because you haven't changed your ballot for any other candidate, if this was the case, then this is the case. By the result being like that for a good election, it will also be the case for the other election. Okay, that was E and E0. Right. Okay. So basically the argument is independence. It doesn't matter how you voted for anyone else. It happened here, it will also happen here. Okay, I will need it in one line, but I should probably skip it. Okay, so now the filter of decisive sets, finally. Okay. Okay, so for any given pair of candidates, look at the sets which do decide that pair. And turns out that these sets are exactly the same for any pair. That will be the second one. Okay, so a bit of notation again. Okay, so let f of AB be the family of sets decisive for A and B. And let F be the family of all decisive sets.
So it's for A over B.
Sorry?
So it's for A over B.
For A over B. Oh, yeah, that's it. And this is the family of decisive set, decisive period, decisive for anything. Right? Again, this is non-empty. If anything else, then the set of all voters is in there by unanimity. But I will show that this is an ultrafilter. I don't need to tell you what an ultrafilter is yet, but this will be the ultrafilter, which will give you the dictator because it's an ultrafilter on a finite set. That will be the rest of the proof. Okay, first of all, the decisive sets for this pair are exactly the decisive sets for any other pair. For any A and B and C, the decisive sets for A and B are exactly the decisive sets for A and C. And, which is the same proof, C over B is the same as A over B, which will be the same proof. And a corollary, I'll prove that now, but a corollary immediately, these sets are exactly the same for any pair. So this family of sets decisive for any pair, to be decisive for one pair is to be decisive for any other pair. For any pair of candidates. My favorite way to read this is the mafia state of politics. If we can vote in this guy over that guy, then we also have the power to vote in any other guy. That's not shocking, but that's what the lemma says. Okay. You just pick a guy. It doesn't matter who the candidate is. If you can vote in a guy, we can vote in any guy. Okay. Proof of that. Okay, so let's see if I mess up the simplest bit, namely the finite combinatorics of a linear order. Okay, so let C be some other guy who's not either A or B, and let that's the third guy, and let an election be such that this set, which is decisive for A over B, is a subset of the preference of now C over B. What I want is to show that in the result, C will be favored over B. I know that A will be favored over B. Okay, so I will build another election, say E prime, such that, now let's see if I mess it up. A and B. Okay, so A, B, let me help myself with the picture I've made. Okay, so what I want is that if C is below A in the original election for some voter, then put C even below B. If you were here, then you drop down here. And if you were above A, right, one of these has to happen. This is the only bit where they are linear total orders. So these are the only cases. So put that below the one. If you are here, that will be A, B, and C. Sorry. A, B, and C go all the way down, right? And if you were at the top, go in between, right? So it will be A and C and B. Do this for every voter and extend E however we want. Just behave like this on ABC. That won't matter because of independence, but behave like that on ABC. Then, okay, I have, if I haven't messed it up, then I have A over C unanimously in this election meeting. Unanimously, that's the way I did. A is over C, A is over C. So these are the two only options. And I have A over B by X because, right. Yeah, right? X was here, right? And so, did I mess it up? Yeah. A over B, B over C. Okay. Okay. Another homework. Should I have done this and say CB instead of AC? Okay. So, no, I did mess it up. Sorry. Let's see. What is it on improvement? Okay. Okay, I messed up the order. Sorry. What I want, the argument is clear now. This is true unanimously. Right. No. I messed up the B and C. This is true by the preference set. So by linearity, right? But I messed up the letters of E prime. So this will also be the case by independence, because I didn't change any other candidates. Sorry, but I messed it up. This is the argument I want to make, but I messed up the letters. Okay. Should I get stuck here? I preferred A over B originally, and now I want to force A over C. Okay, so if C was above A, now C comes below A. And if C was below B, no, and if C was above B, right, then it comes below B. This is where I messed up. Sorry. If C was above A, then it comes between A and B, definitely below A. And if it was below A, then it comes even below B, right? Sorry. C. I still messed it up. Okay, forgive me, I messed up the letters, but this is the idea. If you can dominate, sorry, I'm sorry for stuck in the simplest bit, but if you can dominate this guy by A, then you can dominate any other guy by A. Sorry for messing up the finite combinatorics. Okay, so look at this. How much time? So look at this family finally. Okay. This family of the intersection of all these sides of sets is a filter and is in fact an ultrafilter, and that will give you the dictator. Okay, so one more. This set, which is the intersection of all decisive sets for all pairs, which we now know is any decisive set, is a filter on the set of filters. What is a filter? I hear you ask. Does everyone know what a filter is? Does anyone know what a filter is? Okay, it's simple. It's a natural notion. The notion of a filter, let me define it, captures the idea of being a large subset. In our case, that will be the decisive subset. Being a large subset of the ground set in some sense. So let's say generally, let's say a family, let's call it F again, is A. Well, let me call it the same, okay? Generally, it's a subfamily of some power set, but is a filter if the empty set is not in that family, but the whole set is in that family, because the empty set is not large and the whole set is large. If some set is in the family and some set is even larger, then the larger set is also in the family, so it's close upwards. And also, if two sets are in the family, then the intersection is still in the family. This is a natural notion of largeness. The sets in F are large. This is a family of large subsets. The whole set is large. If some set is large, then any larger is also large. And if two sets are large, then the intersection is still large. The first example of that is the subsets of naturals with a finite complement. That is a notion of largeness on the set of natural numbers, containing almost everything, besides finitely many. That's a filter. What I want to show now, that this is a filter. This is our notion of largeness now. To be large as a subset of voters is to be decisive. That's a notion of largeness. Now, most of that is easy. First of all, the empty set is not there, because what would that mean for an empty set to be decisive? Nobody voted for you, that makes you live in it. That's not the same procedure. The whole set is there. This is precisely the unanimity condition. If everyone voted for you, you are good. Secondly, superset, obviously. I didn't state that, but if your set is decisive, then any larger set is also decisive. And the only one which you actually need to do, I'll call them X and Y, is the intersections. Okay, so let X and Y be in the filter, be in the family. What does that mean? X is decisive, Y is decisive. I need to show that the intersection is still decisive. Okay, so choose. It's a similar argument to the one I messed up here. Choose an election such that the intersection is the preference set, or is at least the preference set of A over B for some A over B. We know already, it doesn't matter which. And choose some other candidate, which is possible because there is at least 3 candidates, such that okay, and an election, some other election, such that, and here comes the argument. Okay, can I write it down? No. Okay, just a picture, but the idea is simple. On the intersection, put okay, this will be put C below both of them, put C above all of them, and put C in the middle of them. That's the ideal. That's the idea. Let me not mess it up like before. Then you will have in your hand an election for which this is precisely the decisive set for A over B, and by that characterization, which I already erased, that will make you decisive. Make it exactly the intersection. Tweak the election so that the preference is exactly the intersection. Let me stop here. Right? Okay, proved. Okay, so it's a filter, but it is in fact an ultrafilter. What is an ultrafilter? An ultrafilter is a maximal filter which decides every subset. What does that mean? That's a filter such that for any subset, either the set is in the family or the complement of the set is in the family. Why this? For example, this is a filter which is not an ultrafilter. A naive example, this is the power set, the power algebra of the ground set. This is the empty set, this is everything. And this is the filter, the family of the large ones. And these are their complements. Okay, odd numbers versus even numbers. Which one is large? Neither is large, neither small. It is infinite and also has an infinite complement. So a filter doesn't necessarily decide everything. An ultrafilter is a filter which does decide everything. This never happens. It's either yes or no. Either you are big or you are small. That's an extreme case of a filter. It's called an ultrafilter. Okay, so the statement now is F is an ultrafilter. As a subfamily in the power set of waters is an ultrafilter. Well, we know it is a filter, so we only need to check this condition. So give me a set of waters. And I'll show you that it either is in the filter or the complement is in the filter. So choose any pair of candidates. We know it doesn't matter. Okay, so choose some election and some two candidates such that, okay, without loss of generality, I can assume that the result will put A over B, or the other way around, but one of those will happen. Then, okay, such that, and this is either the preference set of A over B, or without loss of generality, it is the preference set of B over A. One of these has to happen because the ballot is a linear order. Either you put Ellis above both or below both. Everyone did. So we are either these or those. Okay, but in that case, either X is decisive. These are exactly the complement of that. We are those who prefer Ellis to both. You are those who prefer both over Ellis. Okay, but that's it. That means either we are in the set or the other guys are in the family. It looks abstract, but it's still, imagine the simplest election procedure of all, simple majority. If the election procedure is simple majority, either we are the majority or the other guys are the majority. So this generalizes that to any election procedure. Either us or the other guys who get to decide. Okay, but that's almost it, because this is an ultrafilter, and by this, where is it? By this condition, it is closed under intersections of 2, but you immediately show it is also closed under intersections of 3 and 7 and any finite number. So if the whole ground set is finite, it is closed under any intersection because the whole family is finite. So the intersection of all F, meaning the intersection of all decisive sets, is also in the ultrafilter. But this set has to be a singleton. Why? Because if you're an ultrafilter on a finite set, okay, cannot contain a 2-point set because, where is it? Okay, equivalently, I need to say that, sorry. If you have a set in the ultrafilter and it is split into 2, then either one of them is in the ultrafilter. The proof is trivial. If not, then both complements are there and you are breaking this, or you contain the zeros. So if your set is big and you split it into two parts, one of the parts has to be big. That's trivial. Okay, so if you have you cannot contain a 2-point set because then you split it into two singletons and one of them has to be there, but then it's not the intersection of everything that was in the filter. So on a finite set, this is because the set of voters is finite, which I guess is enough for democracy, but then the singleton, the ultrafilter looks like this. It's called a trivial ultrafilter. Take 1 point, one singleton. These are the 1-point sets. Take that, take every one that contains it. That's it. This is the dictator. And to be large, to be decisive, is to have that guy among you that makes you large. You decide, because that guy decides. That's it. That's the proof. Okay, how much did I go over time? 46. I'm brilliant.
Oh, sorry. I should have been checking it. Sorry.
Okay, so that's it as far as the proof goes. Thank you.
Any other questions?
See how I saved the ultrafilters to do one last half whiteboard? Not too scared anymore now. Yeah.
Of course, when the set of voters is infinite,
Right.
So then you it's not necessary to be a dictator there.
Right. The image generalizations are the ballots are not linear orders but partial orders. The sets are not finite, but you still have an ultrafilter in your hands. Now, not giving you a dictator, but an ultrafilter of decided sets is the obvious generalization. This is the most like thrilling formulation, of course, on a finite set. Okay.
And so what meaning does it have in the infinite case? The ultrafilter?
What do you mean by meaning? What meaning does this have? It's a theorem.
I mean, yeah, but in the finite case you have a dictator, but there's the argument that
No. This is the only thing that breaks in the infinite case. Like everything else works, except the intersection is not a singleton. That's the only statement that doesn't hold.
May I answer? So, looking at quadratic theory, there are formally finite sets, but no, there are formally infinite sets, but these are sets which contain some vague part. Such part we don't know about the voters, or do they vote? So it's formally infinite, but in fact it is a model of finite situation. And in this situation, and I think we can apply it to the real world. Sometimes we don't know about all voters. So this is.
I was a bit scared about the Volpinka argument, seeing you come here, but yeah, his original motivation was the capital market. By the way, there's the PDF, the original PDF of Arrow is still available. It's in the 50s, and he was an economist. And his application was that the ballot is your investment on a capital market. I'm willing to put this much money into this stock, and this much money into this stock, and this much money into this stock, and I'm not putting any money into anything else, which is finitely many. And that casts a bullet. Like that's my order of preference. That's a linear order of preference. How much capital do you invest in what stock? That's the vote. I chose like voters and candidates because that's something you can relate to, but the original application is different. Investing. Even calls it social welfare, like choose the most good for everyone. Bloody do good, right?
So I might have a question. So there is some, I mean, Dushan will know much better than me. So the voting theory, right? There is some standard theorem that is if your voting system satisfies 1, 2, 3, 4, 5. So these were only 3 conditions. I remember the other thing had 5 or something.
I don't know anything else about voting theory. So
there are many.
Right.
This is my lecture number 4. And
Okay.
So you have that in game theory, voting theory.
Yeah.
Okay.
There are
Right. No, I just thought
Or that's another homework.
if the others rely.
Take the 3 conditions and pick one guy in beforehand and make your election procedure. The result will always be, well, what this guy said. Is that the same election procedure? Well, unanimity, yes. If everyone said so, then Joe also said so, and that's the result. Nice. So if monotonous, well, not only he said so, but more people, yeah, it is monotonous. And is it independent of our candidates? Well, it is independent of anything. It's what Joe said. So yeah, it's the same. Those are really mild conditions. Like doing what Joe said is the same election procedure. It's not. In the real world, even more so. Nobody voted for you, but you're still the president.
No one knows who is Joe.
No, pick him.
This is the problem of the theorem.
Yes.
You don't know who is the dictator.
That's what I mean by a cheap thrill. There is a dictator, but you only know that after the
guy is not aware of it.
Right, he doesn't even know he's the dictator. So in the next election, and they do what? Faculty Senate do vote, and then check if you are the dictator. One of what has to be, the theorem said.
Okay. So that's not it. That's all. Then thank the speaker.